Good afternoon, everybody. It's a great pleasure for me to participate in this webinar series. I'd like to thank America Medeiros for inviting me to give this presentation. We agreed that the title of the presentation should be Important Gastrointestinal Hermeneutics and Current Issues for Control in Germany, maybe to give particularly the European perspective. And I added here and beyond because I'd also like to present to you some data we, together with others, generated recently in Africa and in Spain. So what we are going to look into is, first of all, a brief repetition of what is essential concerning gastrointestinal strongholds, such as Osteotagia, Homunculus, or Oncovera in cattle. Then I'd like to discuss with you detection and economic effects of worm infections in cattle, move over to current treatment and antibiotic resistance issues, and finish with sustainable approaches for worm control, finally wrapping up in a summary. Gastrointestinal worms in cattle are mostly and mainly represented by trichostrongylus, and their appearance, as the name already says, is very small. They are up to 3 centimeters long, with Homunculus being the largest one of this group. They are thread-like. The males have a particular ending, bursa copullatrix, as you can see here, with 2 spicula, which help the male to widen the vulva when they copulate with the female. And this structure here, together with other features, allows us to do a species diagnosis. Trichostrongylus occur on every cattle farm where cattle are being kept on pasture. The localization of these species differs depending on species. We have a group which is residing in the upper mesum, listed here, and another group which is residing in the small intestine. I also listed Toxocara vitellorum here, although it's not a trichostrongyle. In Germany, at least it's very, very seldom occurring, but it can occur. It's a special parasite. I think in other parts of the world it's more prevalent than in Germany. What is generally the case with all these species is that they don't occur as single species isolated infections, but in mixed infections, and that also of course complicates the clinical symptoms you can see, because they all differ in their pathogenicity. How often do they occur in Germany? Some data here just showing here the white columns, the prevalences when examined in beef cattle, ranging around 40% if you look only once per year. If you look repeatedly in the same age group, and that is listed here, from spring, summer to autumn, then you can see infection rates of about 2/3 of the examined animals. That is certainly less than, for example, in Brazil or in Argentina, where you can anticipate often a much higher prevalence. And in general, if you would examine the individual animals several times, I think also in Germany the overall prevalence will be higher. However, the infection intensity in principle in Germany is certainly less than in Southern American or also Northern American states. Just to repeat the life cycle, and I brought you here a picture of the life cycle of Osteotagia. Osteotagia is the most important gastrointestinal parasite, at least in Germany. It has a rather high pathogenicity. It occurs mainly in beef. It's small, just 1 centimeter. It's pre-patency period, that is the period between uptake of the infectious 3rd stage larvae till the shedding of the first eggs is 3 weeks, and it's localized in the upper mesum, where the larvae after excitus migrate into the mucosa, and in the glands there they develop to 4th stages before they then move back into the lumen of the upper mesum, where they develop to adults. And in this phase already they cause significant changes which lead to disease. What they can do, at least in some areas, they can stop their development. In Germany, over winter, after larvae on pasture, where they develop to third stage larvae, have been exposed to low temperatures, below 8 or 10 degrees, they will then, when they being taken up, not perform their development within the 3 weeks, but inhibit their development. This is a phase of hyperbiosis for several months until the conditions in the environment following winter in the next spring are good again, and then they'll start finishing their development and shedding eggs then early next summer. So what do they cause? They cause, as I already said, during the mucosal phase, a change of the appearance of the mucosa, cobblestone-like mucosa you can see there, and the development in the glands leads to the degeneration of parietal cells. They produce HCl, and that leads then to an increase in the pH. Pepsinogen is not activated. That leads to a reduction of protein digestion, loss, that should say, of bacteriostasis, and also secondarily then pepsinogen secretion increases, and we find more pepsinogen in the blood. Also gastrin secretion is increased, also that you can find then and use as a diagnostic criteria in the blood. Further on, then the secretion cells are then lost, and instead undifferentiated cells appear. And what is very important, you have also a loosening of the tight junctions, and that contributes to plasma protein loss into the lumen. Finally, resulting in hypalbuminemia, reduction of the oncotic pressure, and then edema you can also see in chronically diseased animals. Clinically, this leads to emaciation, poorer meat-fat ratio, which cannot be fully compensated even after successful elimination of the worms. That's something which the animals will also be suffering from. That is the clinical picture here. You see here this cobblestone-like mucus where the glands are enlarged, also here. At least in Germany, we can in principle have two clinical pictures. One is summer osteotociosis, and the other one is winter osteotociosis. Winter osteotociosis happening in single animals, as I just said, after the phase of inhibition in the next year, after the first grazing season. We don't see that very often anymore, so I suppose in many areas of the world you don't see it at all. So the major clinical disease picture is the summer osteotociosis, which comes along with acute infection disease. Usually all young animals of a herd, first season grazers, are being diseased. In Europe, it's the summer season between July and September where this occurs. And you see a non-bloody diarrhea without fever, brownish shaggy coat, inappetency, and these other symptoms. Desiccation can also occur, and in individual animals it may even lead to death. And this is a picture of the diarrhea you see here at the rear end of the infected calves. Diagnosis of this disease is being achieved by coproscopic analysis, but you can also, of course, get a hint already by the clinical manifestation. If necropsy is being performed and you perform a decent parasitological examination of the content of the intestine, you can also see the worms there. But the standard method of diagnosis is, of course, the coproscopic detection of the eggs, as you see them here, a little bit more strongly magnified here, with the thin-shelled eggs, about 80 centimeters in diameter, and with morular stages if they are shed freshly. Later on, even within a day, you'll find a larvae there, embryonated there. This is a less intensive magnification picture here. You can detect these eggs by using the flotation method, either qualitatively or quantitatively. Quantitatively, the most well-known method for a long time has been the McMaster method. Other methods have been used as well, like Flowtech or FactPack methods. Many different tools you can use. What is important, because this is also of course quite effort intensive if you do it animal by animal, is the information that you can group together the samples of, let's say, up to 10 animals. Several studies have shown that a composite sample of up to 10 animals from the same age group gives a meaningful result, representative of the mean of the 10 individual samples. And it's much less expensive and therefore a very good monitoring instrument. Additionally, what I'd also like to point out is there is a serological test adapted to use milk, bulk tank milk, and we'll see data on this very meaningful test as well later on. Yes, later on is already now. This is now the move to the cost effects of helminth infections, and one nice illustration of this is shown here, where the colleagues who have developed this bulk tank milk ELISA in Ghent, in the group of Joseph Kreuzer, together with Scanis Shaghi and others, have put together a lot of data they've gathered during the establishment of this ELISA, when they went onto different farms and compared the optical density ratio they obtained with their ELISA, shown below here, with the milk yield and on the farm. And you see here from a ODR beginning at 0.6, the milk yield starts to decrease the higher the ODR gets. So the more antibodies they find in the milk, the lesser the average milk yield on the farm was. A good association correlation between bulk tank milk data and milk yield per farm here. You can nicely use this instrument to monitor the treatment need as well on the farm. That's what we also did in a study here in 3 countries in Europe. Together with Thomas Gurden, we examined farms in Lower Saxony, that is here in Germany, but other colleagues did it in France and in the UK. And I'll only talk about briefly the German data. We went to 28 farms with about 435 animals, and we used moxidectine for treatment in these animals. They were being treated 77 to 7 days before calving, and you can see here the optical density ratio mean on these farms was rather high. I just told you that starting at 0.6 the ODR becomes positive. They were not all, but many were above this threshold. We performed milk yield data recordings or used the data recordings together with the ODR for 335 days. And the statistical analysis showed us that particularly in primoparous cattle, we'll find of milk yield of 2.3 kilogram per day in these Osteotociosis infected farms when they received moxidectin compared to non-treated control animals. So coming to the treatment, there are several groups of active ingredients available. However, none newly developed drug class during the last 30 years. So we still have the 3 drug classes: benzimidazoles, macrocyclic lactones, and the levamisole is a representative of the tetrahydropyrimidines. And while previous recommendations for treatment were saying that you should always treat the whole group, now more and more targeted and selective treatment approaches are being discussed, and we go into that a little bit more in detail later on during this presentation. At least in countries where you have hypobiosis induction of trichostrongylus, you should always in autumn treat the animals with either fenbendazole or macrocyclic lactones, as these are effective against the inhibited stages. And more and more it's important that you check the efficacy of your treatment, for example by using a fecal count reduction test, or that this is the state-of-the-art test. I'll come back to the selective treatment later on. In addition to the treatment for control, it's important to perform pasture management that may include late turnout of calves combined with mowing of the first growth, where this is economically feasible, and in Germany often that is. Separation of calves and older animals, and yeah, of course, the prevention or at least attempts to postpone antibiotic resistance development, for example, by using selective treatment approaches. Just briefly, one comment on how do you perform fecal air count reduction tests. We and many others together have just also in the context of the cost action COMBA provided a short guidance, a protocol for fecal air count reduction test frame conditions, but in practical you perform a quantitative fecal sample analysis using either McMaster, miniflotic or FACPAC methods, and treat the same day. You should at least use 10 animals, and then 10 to 14 days, depending on drug class you're using, you're going back to check the quantitative account again, and you expect a reduction, depending on the drug class, if it's a macrocyclic lactone of at least 98 or benzimidazole at least 95%. We've performed this repeatedly in Germany in different regions. The first study was performed in 2007 to 8 and published in this paper here, where together in a EU program with colleagues from Belgium and Sweden, we tested the efficacy of macrocyclic lactones and benzimidazoles in farms, and we found that macrocyclic lactones were not effective anymore on at least 3 of the tested farms, of the 6 tested farms we analyzed here, while the benzimidazoles we used, the benzimidazole we used was fully effective on all the farms we tested it on at that time. A few years later, with Thomas Gurdon again, and together with countries, other European countries, we performed another fecal air count reduction test, now using ivermectin and moxidectin on 12 farms, and we found full efficacy for moxidectin only on 4 farms and for ivermectin only on 2 farms, and 1 farm with clear resistance against both drug classes, as you can see here. And the most recent study we performed is shown on this slide here. It was performed in 2019 by Mrs. Schramm here in the northern parts of Germany, and she tested on 11 farms macrocyclic lactones as the farmers would use them, and here from the 11 farms there were 6 farms where we found clear indication of macrocyclic lactone resistance. So we have a problem there. It's not so apparent to the farmer because it's mainly Coparia parasites which are being resistant here, which are not so pathogenic like the Osteotociosis worms, but globally there's also reports on Osteotociosis resistance coming up here, and if that is going to increase and spread, then farmers will really become more aware of this issue and see the problem coming up. So I said I'd also like to present to you some data from Brazil, and this is a just very recently published study in preventive veterinary medicine, a collaboration with Fernando Borges and his colleagues, performed during her thesis by Flavia Favero, all coming from the Federal University of Mato Grosso do Sul in Campo Grande. And yeah, Flavia visited over 60 different farms and collected fecal samples there, and performed larval cultures, then analyzed macroscopically which parasites are there, looking particularly into the genus of Haemonchus, because that's what was the most widespread parasite there. All farms were positive for Haemonchus placei, and some also showed Haemonchus contortus, that is the blue and greenish parts here, some also Haemonchus similis. And then we looked into the benzimidazole resistance associated beta-tubuline SNPs here, and in 11% of the farms we found increased BZ resistance associated alleles. And yeah, to finish with this slide here on a study also very recently written together, not even accepted. It's under review currently. This study here performed in Sudan in the South Darfur region, where Khaled Mohammed Zali performed a study on doing a fecal count reduction test. And in 3 out of the 5 South Darfur regions, he found using benzimidazole, albendazole is a drug, reduced efficacy, fecal count reduction ranging between 85 to 94.6. And we, in this case, also looked into the beta tubulin SNPs usually associated with resistance. What we didn't find was a big increase in the codons 167 and 200, but in codon 198, and also there it was predominated by the exchange between, in this position, to leucine. In post-treatment samples, they all showed this leucine and codon 198, which is a rather new finding. So, finishing up with the aspect of refugium, why do we have to, and what do we understand under the term refugium? It's a proportion of the worm population which is not subjective to enzymatic treatment, could be the free-living larvae on pasture or stages in the host which are not affected by the drug. How can refugium be maintained? Targeted selective treatment, that's the solution there. That means only a part of the herd receives treatment, either those which are most sensitive or those which contribute most to pasture contamination. And just very briefly, a cartoon who can show you the effect. This is the total worm population represented by the intrapopulation in the single animal, and the superpopulation is then that of the animal together with the pasture. That is all together. We have sensitive worms, they are blue, and resistant worms, bad worms, which are red. And in conventional treatment, if you treat all animals, the surviving worms in the treatment animals will all be resistant or offspring of resistant worms, and that certainly will increase to a much faster increase in the proportion of resistant worms in the environment as well, as if you perform another approach, which is the selective treatment. If you treat only one animal, then out of the two, then the other one will shed also susceptible worms, and so the increase in the proportion of resistant alleles and worms on the pasture will be much less fast. This approach can be also used, it has been established first in sheep, but now also there is data on its use in cattle, like this study here from the UK, where colleagues used this approach on 3 commercial farms with 104 calves in total, and they performed just monthly weight determination as an indicator for treatment. Treatment was only done if an animal which would be below the threshold of 0.7 kilogram monthly per day increase by the monthly measurement would be treated. And by using this approach, no animal was treated more than once, and still the overall herd increase in weight gain was achieved, and there was no reduction in productivity and a very drastic reduction in enzymatic treatment as opposed to conventional treatment approaches. So that's practical and also safe, and we should more and more recommend this treatment approach to farmers in the field, I believe. So to summarize, gastrointestinal strongholds, and I put here also liver fluke because that's important, at least for Germany, continue to be very common in grazing cattle, and that is why parasite monitoring from farm to farm and monitoring the efficacy is important. At least under the German situation, where we don't have very high infection intensities, Significant reduction in milk yield is probably the main economic consequence of Helminth infections in dairy cattle. Deworming of animals on farm with on those farms with high infection burden, and to identify those you can use milk testing, and then you'll be able to do targeted treatment, results in significant increase in milk yield, so it really pays off to do this on specific farms. The efficacy of macrocyclic lactones is increasingly limited by resistance, and you should at least every other year check the efficacy of the drugs used on the farms by using the fecal count reduction test. The efficacy of benzimidazoles generally still high, other than in sheep strict strong girls, but there is also a beginning issue of resistance with novel beta-tubuline SNPs we haven't seen so far before. And as I said just before, targeted selective deworming is a practical and safe concept